Okay, I'm sorry. There's some confusion. Okay, I'm very glad to be speaking at the meeting. I recall my visit to Chile very fondly and seeing Jorge again after a long time. So let me get on with it. I've delayed it. So now it's 6:17 here. So I have 15 minutes. Okay, I'm going to speak upon this topic here, and I'll begin by giving a very short but strong motivation why infrared free or asymptotically strong gauge theories, Yang-Mills Higgs theories, are interesting, in particular supersymmetric ones. And this class of theories obviously is something which is near heretical, and very little attention is paid to them. They are thought by many to be just too scandalous and not worth pursuing because they are inconsistent. But given that we have a very large, an important class of supersymmetric guts, rather the most successful class of supersymmetric guts are asymptotically strong, the motivation is that one does need to see if one can say something about such theories. And I'm going to argue that in fact there is available a formalism based upon what is called the generalized Konishi anomaly that allows you to derive the gut symmetry breaking waves using that formalism. In analogy with infrared condensation in the well studied infrared strong theories, which obviously cannot be realistic. But on the other hand, supersymmetric guts the scale at which they become strongly coupled, the theory is effectively exactly supersymmetric, so that one would hope that supersymmetric techniques are easily applicable. So then I'll set out this dynamical supersymmetry breaking scenario for asymptotically strong guts. If I even manage to get that far, that will be an achievement. And then I'll describe some details. Okay, so let me go on with it. So the minimal supersymmetric SO10 guts based upon somewhat large Higgs representations, like 126 bar and 210. Rabi Mohapatra and I have been studying them for near on 40 years, along with many other people later. And they are optimal supersymmetric guts. They have many virtues, which I don't have time to go through. They are realistic, parameter counting, minimal, calculable, predictive. They have a renormalizable seesaw 1 and 2. They support inflation, and they have an R parity protected LSP, dark matter. They have controlled B violation. So basically, they are phenomenologically successful, and they are minimal in the sense they are parameter counting minimal, and therefore they are champions, even if we are saying so. But they are well regarded in the gut community. Unfortunately, they also have one glaring sort of fault which their opponents throw at them. They are asymptotically strong. The beta function is huge. It's greater than 109. So therefore, just above the perturbative unification scale, you have a Landau pole. And that obviously is regarded as bad news. And so one would like to one is faced with this choice that either you give up this successful grand unified theory, which has all these virtues, or you face the fact that very quickly it becomes the gauge coupling blows up and other couplings. So this is a perfectly supersymmetric theory, as I said, but the Landau pole makes you, wonder. So the motivation then is that the phenomenological success is the message that you should consider this problem seriously and try anything you can to make sense of it. And basically, there was an intuition that I had way back in 2003, where I proposed that the strong coupling dynamics of the gauge theory at the Landau pole drives the supersymmetric spontaneous breaking of the grand unified gauge group down to the effective theory of the minimal supersymmetric model. And of course, analogous things would happen for other asymptotically strong theories. Now, there are very well developed techniques based upon the holomorphy of supersymmetric gauge theories. You could call them cybergistics, which are available for asymptotically free theories. That means infrared strong theories in their Landau pole regime, where the gauge groups condense, but you get supersymmetry preserving condensates in the effective low energy theory. And the idea is to proceed by analogy. And as everybody is aware, Veneziano and Yankelowitz in 1982 showed that pure supersymmetric Yang-Mills theories, due to their Landau pole, they support a gaugino condensate, a gluino condensate, if you like, or a gaugino condensate. And the scale of that condensate is set by the scale at which the gauge coupling has an infrared Landau pole. And that scale I'm calling lambda, which you can derive from the beta function. And because it's infrared strong, therefore this, if even if you have a small coupling at higher energies, it will diverge, as we all expect. However, because of the supersymmetry, the usual gauge field condensates are not supported, but instead you can support a gluino condensate. And the gluino condensate is a part of the square of the gauge chiral field, W alpha, and the product of two of them, or bilinear of them, is the glue ball field S. And the leading term in S is, or rather its vacuum expectation value, is then the cube of the Landau pole scale. And this is described by the Veneziano-Yankelowitz superpotential. Extremizing that, you can get this thing. But well, I don't think there's much content to that. That's not dynamically derived. That's just a representation of the assumption that the dynamics can consistently support a condensate. There was a this was the what I knew in 2003, and there's also a Konishi anomaly relation based upon the supersymmetric generalization of the triangle anomaly to where you scale the chiral fermion, the fermion inside a chiral field of just one chiral field. So for each chiral field in the theory, you have this equation, whose generalization we will look at a little later. And I was able to show that, well, maybe there is a condensate, but I couldn't go much further with a toy SU2 model. Very strangely, right, a few months after I gave up the problem as being too beyond my powers, Cachazo, Douglas, Seiberg, and Witten wrote an amazing paper on the phases of UN super Yang-Mills with adjoint matter. And they, in fact, developed a technology that allowed them to calculate all the condensates in this theory in the infrared strong regime. So basically, the theory has a superpotential of degree n, and the zeros of the superpotential label arranged on the diagonal of the web of the adjoint field label the vacua, the possible vacua in the low energy theory, at least in the semi-classical limit. In the strongly coupled limit, we'll see that there is a more general description. So in such a theory, there are these gauge invariant chiral operators formed from the powers of the chiral superfield and products of that with the glue ball superfield. And these generate what is called a chiral ring, in which the multiplication is defined modulo commutators with the anti-supercharge. And you can also show that the gauge field and the matter field, they commute with each other modulo this commutator. This forms a chiral ring, and that gives it amazing properties. So what they said was that the quantum phases of the low energy field theory are labeled by a vector of integers, which tells you how these, in the semi-classical limit, it tells you how these zeros are distributed on the diagonal of the wave. But in general, they are just a set of integer parameters. And then they showed that, firstly, that supersymmetry implies that the chiral ring correlators are position independent and fully factorizable. And moreover, a generalization of the Konishi anomaly shows you that if you consider chiral transformations, I'm sorry, this is miswritten a little bit. This is Fi.
5 minutes left, say, Charan.
Yeah, okay. So Fi. So arbitrary variations of the chiral field dependent upon itself and upon the gauge chiral field allow you to get a relation between the wave of the derivative of the superpotential multiplied by the variation and a product of the glue ball field and a certain combination of the derivative of the variation. And this is a generalized Konishi anomaly equation, and it's very powerful. So using this, they defined a set of resolvents which collect together all the chiral ring generators. And using the Konishi anomaly, you can derive equations, loop equations they're called, for these resolvents Rz and Tz. And these loop equations can be solved, and what is most important is that they define a certain generalization, quantum generalization of the derivative of the superpotential. And that generalization actually is a branched function, so it defines a Riemann surface. And you can then solve the for Rz and Tz in terms of two polynomials and the constants in those polynomials. So that's Cz, which is a polynomial degree n minus 1, and Fz. And say we work with a renormalizable theory in renormalizable guts, then the constants are basically the leading condensates, the glue ball condensate, and the first one beyond that, which is S times phi, and then the condensate in Cz. Okay, so Cz is also here. So the Cz contains this T1. Uh, okay, so some details. So this superpotential, quantum superpotential derivative, you see, depends upon F. So if the condensates, the gluino condensates go to 0, then Y reverts to the classical value. And the higher values of these chiral generators, which are not present in F and C, are determined by these Konishi anomaly relations. So the Gaugino condensate, as we said, sets the scale, and y squared being a degree 2n polynomials, its zeros are bifurcates of the classical critical points. So these are the A1 and A2 are the classical critical points, and this is these when you turn on the quantum effects, you get branch cuts connecting the bifurcates. They bifurcate because you have double the number of zeros, and these basically act as the A cycles of the Riemann surface. And then you can extract the generators of the chiral ring overall condensates by taking contour integrals around the contour at infinity, which encloses the point at infinity. But you can also extract the condensates in each one of the in each one of the factors of the symmetry group. That means the condensates for SUN1, SUN2, and so on. You can extract them by taking contour integrals around these branch cuts, so around the A cycles. So this formula, encapsulates that. I obviously don't have time, so you do contour integrals of powers of z times tz. Now, the whole idea is that formally you can carry over this entire adjoint type analysis, even if the adjoint, instead of being for SUN n cross n bar, is r cross r bar, where r is a representation larger than the fundamental. But as soon as it's larger than the fundamental, the index starts growing very rapidly, roughly as the square or a higher power of n. And therefore, for example, if you take the symmetric representation of SU3, you will find that B0 turns out to be 21. And therefore, the theory is asymptotically strong, but all the formally everything carries over as it is. So what we envisage is that the broken low energy gauge symmetry associated with the expectation value of phi, which defines the weakly coupled theory below the scales mx and lambda. And we propose a formula which is not very interesting for infrared strong theories, but for infrared weak theories, like the ones we are interested in, Classically, this integral will simply pick out the wave, or ni times the wave. So you divide by ni and that cancels out. But quantum mechanically, because y is a branched function, you will get a quantum wave. And you can show that these definitions are consistent, which I don't have time for. You can define what I call an effective superpotential, which in whose extrema are these quantum waves. And therefore, if you use that as the starting point for your spectra calculation, you get consistent results. A simple example, as I already mentioned, is that you take this representation R, which is called the base representation, and then phi would transform as 6 cross 6 bar. And then you can work out that the possible patterns of distribution of the two quantum waves that you have available to you, and you can get various symmetry breaking patterns and various spectra, which again, I don't have time to discuss. Now, for a gut model like SO10, you need to reduce the rank, and therefore you need to add some more matter in order to reduce the rank from 5 to 4. And you can do that by taking either QCD type things like Q bar, or R cross R symmetric, R bar cross R bar. You can also do, I have two transparencies. You can also do the anti-symmetric case. So if you introduce these, you can reduce the rank. And now
Und der andere, der da drunter, der hat sein Deckenlicht, aber der da drüber, Ishikawa.
Sorry, is somebody...
Sehen die Leute das nicht?
Please mute your microphone, please.
Yeah. So I'll conclude with the realistic ultra minimal SO10 MS gut type model, that you take the base representation to be the 16 plate spinner of SO10, then 16 cross 16 bar will give you adjoint type multiplets, and the whole thing, you retain that and use that for as your adjoint type multiplet. But you also use for rank breaking 16 cross 16 symmetric and 16 bar cross 16 bar symmetric, which contain the other important multiplets of the minimal supersymmetric gut type scenario. And using a basis, where you, based on the MSSM kind of labels, you can compactly describe that in each one of these sectors, you can assign vacuum expectation values according to whether they are, multiple or they're MSSM singlets, and that adds up to 16. So you have 16 possible webs, but some of them are equal because the MSSM has a gauge symmetry. And similarly, you can assign MSSM preserving rank breaking webs. And this achieves breaking to the MSSM. You can calculate various things, which I can't describe to you here. And you can fit fermion masses. Interestingly, you have actually two 10 plates here coming out from this. And therefore, you have couplings that you don't have in the MS gut, because you've retained also all this other content over here. And you can, so therefore, my final transparency is that analysis of the chiral condensate system in asymptotically strong guts using the generalized Konishi anomaly relations realizes spontaneous symmetry breaking with robust dimensional transmutation. I didn't show you that, but even if you put the mass parameters in the superpotential to 0, so that you have no classical mass parameters, but you only have a weakly coupled gauge coupling at some scale below the unification scale, even so, you would, or at the perturbative unification scale, you generate a scale which is the Landau scale, or the Landau pole scale. And that Landau pole scale sets all the webs. So this is a robust dimensional transmutation. Obviously, I can't calculate the dynamical condensates R0 and R1, which I don't know, you have to do it on a computer or some other means. But I can take them as parameters, and then the picture seems to be consistent. So this is a completely novel method of supersymmetric gut symmetry breaking. And the phenomenological, the generalized Konishi anomaly also implies large correlators of light fields, of trilinear correlators. And the meaning of that, I'm not able to extract at the moment, but that needs input from people. What they could mean, or do they disqualify the whole picture, or what do they mean? So this is a vast class, much larger than the class of asymptotically free theories, and I think it bears analysis, and it would modify the basic paradigms that we operate upon, which is of infrared strong and of spontaneously broken theories, and add to it an additional paradigm where you have an infrared weak theory, but a theory which is strongly coupled at small scales, which after all, I don't think is such an unusual situation in physics, that you look at the long wavelength modes which are weakly coupled, but at short distances, the theory is strongly coupled. That is an extremely common situation in condensed matter physics, as far as I understand the situation. So with that, I'll thank the
Thank you very much, Charan.